UCLA, and now he is with our mathematical sciences department here, and that's all I have to say about it. Dr. Scott McCalla.
So clearly this is a pretty awkward room to be talking in, but I'll probably try to stay more or less over here, so you can mostly see me. This is quite full for a teal room. Okay, so title is Patterns Everywhere. Basically the goal of this talk is to give you some idea of kind of the most standard way that patterns form, sort of mathematically, and how we try to understand them. Okay, and so there's just a couple ideas I'm going to try to get across that are fundamental for patterns. And these are going to be an idea called diffusion and an idea called resonance. So we're going to start with basically me showing you the type of patterns that we're going to talk about here, those that I care about most. Because there's a whole lot, like there's patterns on this ground. Okay, there's nothing interesting to say about those. This was some artist put down swatches of carpet as they saw fit. But then there's a special class, more or less those that basically form out of nothing. So nothing is deciding that a pattern should form of a certain shape or size or type. Okay? They just spontaneously emerge. So these are emergent phenomena on systems that otherwise there's no reason that anything interesting should occur. So I'm going to try to describe the type of patterns I care about. Then I'm going to try to describe some of the underlying kind of key ideas you're going to need to understand. A couple historical facts about those who came up with these ideas, and then I'm going to move into more modern research and things that are actually being done here on campus. So that's roughly the overarching path. Okay. So now I get to walk all the way over here. I want to start with more or less patterns in non-living things. Okay. So any of you gone to Yellowstone and just seen these big hexagonal basalt columns on the side of the road peeking through? That's the same sort of thing as here. So we would call these hexagonal patterns. This is the Giant's Causeway, so this is in Northern Ireland, and you just have this huge area around the coast that looks like these columns just all around. You can walk around it, goes up and down, it sort of continues. And this is basically from lava flows that get quenched as they're cooling, and you get these really nice regular patterns that pop up. Okay. So this is one type of just sort of spontaneously emerging pattern when there was no reason for them to exist. So another one here is sand dunes, right? You get wind driving, and basically you get these nice ripples all across the top. And they have these little things that we would call defects. Okay, this is, you imagine you'd like perfect stripes to come out of whatever mechanism is creating patterns. Sometimes stuff fails, right? That's the rule. Okay, so these are called defects. And it turns out often in settings like this, those defects, they'll actually move over time. You'll have them growing or shrinking towards each other. And it turns out that's very, very hard to understand. And then on the right, these are what are called ferrosolitons. So this is a fluid that's magnetically active. It's actually really expensive, but I think it has a ton of iron in it. Okay, sorry I'm moving around so much. I'm sure that makes sense.
No, you're good.
But the idea here is this is what we would call a spot. So these are what I call space-filling patterns. They just fill up an entire domain when they occur. But you can also get what we call localized patterns. So things that are in small little isolation and go into something flat in the background. And then this is what we would call a hexagonal array of these spots. And so how these form is you have this weird magnetically active fluid, and someone just puts a really, really strong magnetic field across it. And it turns out if that field is strong enough, the fluid doesn't want to stay like that. It's not energetically favorable. So what happens is the fluid itself actually buckles into that weird peak-shaped thing you see there. Okay? And it turns out that just sends all the magnetic field lines through. Okay? So these are all what we would call stationary patterns. The ones on the left are space-filling. The ones on the right are somewhat localized, at least the bottom right. Okay? So this is one sort of pattern we care about. But a lot of patterns aren't stationary, okay? So these are what are called oscillons. Both experiments here are very, very similar. This one's just thick clay, and this is a bunch of very uniform beads, right? Turns out, if you shake this up and down really fast, but at the right frequency, it doesn't stay flat. You start to get these weird little bumps. And the thing is, they go up and down in a fairly stable way. So this thing, it's a moving pattern. It oscillates in time. It's periodic. But it stays put. There is a way that you can think of this as stationary. Okay, so a lot of patterns that we think of, they're still moving all the time. All right? And they just sort of naturally emerge. This one is little grains of sand, and you actually get that spiky up and then a weird dimple down. But these things stick around for a long time, and you can get all sorts of different, basically what we would call multiple solutions. So this is 3 different bumps that stay together. Okay, but you can get 2 different bumps that stay together, you can get 1, and these don't go up and down at the same frequency or vibrating. Okay? So these are oscillating patterns. It's not quite in the same vein, but I assume some of you like to ski. I've known of people that actually got asked questions along the lines of where do they store the moguls in the summer? And right, these are one of these things where you have a bunch of skiers going through, but moguls basically emerge from that. And it turns out they also move. Every time someone skis, they push some snow down and it packs on the upper side of that mogul. Those moguls drift uphill over time. So these are dynamic patterns that you can sort of treat like stationary objects. I did not expect standing room. Okay. So all of those were non-living things sort of in the natural world that occurred. Here, this isn't a living thing, but this was basically a chemist's idea of a good analog, okay? So in nature, we have a whole lot of individual cells that have some sort of chemical reactions happening inside them. And then you have cell walls that are barriers, and you have some sort of slow communication across cells, all right? So a chemical system that is meant to approximate that is basically you have an oil, and you make this emulsion of chemical reactants in it. So in other words, I just have a fluid, okay, which is more or less some goopy oil that has all of these little micro-sized balls of fluid suspended in it, okay? So individual balls of fluid that are surrounded by oil and some big mass. Turns out this is effectively what homogenized milk is, okay? When you buy milk at the store, the fat doesn't separate out. All they do is send that through a really, really fine nozzle at high pressure, and all those fat globules break down into very tiny things that are now stable, okay? And what they put in there is a chemical reaction that basically can do different things. And then what you have here is very slow ability to diffuse across this oil between these little balls of fluid. And what you can have is basically a reaction here will slowly influence reactions over here, and over here, and over here. And they can control things like the concentration, how far that distance is in the oil, and other things, and more or less they have some parameters they can take. And so in this setting, these are called microemulsions. They were meant to basically be simplified cell models. If you grow this up and start imaging basically those chemical reactants in some way, so these are different phases for a reaction, you start to get, again, this is what we would call hexagons, or a bunch of spots together. You get these more labyrinthine patterns, which are somewhere between nice stripes and spots. Okay, so that's what we call a 2-dimensional pattern. And it turns out you can start to try to image these things in 3 dimensions, so that's what's happening here. And you see the same sort of patterns form. So instead of hexagonal scalings, you now get all of these basically little balls in free space. Or you get these sort of fingery things and other stuff. The top here, by the way, these are experiments, and these are numerical models for what are called reaction diffusion equations, which are going to be really important to us by the end of this topic. Okay? And I should mention, experimentally, how do you actually image a 3D pattern in basically what is a test tube? You shoot light through it, same way they use gamma rays at the airport, but the same way they image you. Okay? So this is called optical coherence tomography. What these are is basically they take slices down and they shoot a bunch of light, look at the scatter, and then they can reconstruct a 3D image. Okay, so it's called an OCT, and we actually have one at the Center for Biothermal Engineering. So these are still not living things, but these are simple models meant to reproduce the same sort of pattern-forming behavior you see in living things. Turns out you see patterns in living things too. So now we're at biological systems. Okay. So first, everyone is familiar with basically different patterns you get on the coats of animals, right? Like the animal on the top, that cheetah has a bunch of spots, or the zebras have stripes. Turns out if you look at territories of predators and prey, so look at concentrations of prey versus predator animals, you'll actually see nice patterns where things live separated out. Okay. So even at that level, ecologically, these things obey different simple pattern forming systems that you can still look at under the same sort of equations we're going to talk about. Turns out if you look at burglary crime data, you get what are called hotspots. So this is like those ferrosoliton spots. Basically, okay, I have a question. If your house is robbed next week while you're out, a week later, is your house more or less likely to be robbed than it was, say, today?
You wouldn't think it would be robbed again. You wouldn't think it would be robbed right after.
You said more?
I'm thinking more, you know, hit it once, hit it twice.
That's correct.
Yeah,
Actually.
that's good.
You're much more likely to be robbed again by the same person. They went in once, they know how to get away, they've already cased everything, and they know what they missed. All right, so in interviews with burglars, that's actually why they go back. And often you have a neighborhood that is conducive to it. So cul-de-sacs are bad, nice roads that you can get off easy are good, for example. And so that leads to self-excitement, and so you get what are called burglary hotspots. So these are basically localized areas of crime. This is Chicago data on burglaries. Okay? So human behavior leads to these weird pattern-forming phenomena. These are called fairy circles. Okay? And these occur basically in the Negev Desert in Africa, but also in Australia. And there's been pretty heated and hot debate over the cause of these for the past 20 years. Okay? And you'll see them referred to in basically Wall Street Journal, New York Times, Washington Post all the time, because this is some continuous evolving spat, which is ridiculous. And so fundamentally the question is, what causes these basically dirt patches in the middle of a grassland to occur? And they look pretty regular. They're not exactly like those hexagonal patterns. They have different radii, but they're very regular and they spread out for huge distances, just like that. Okay. So, I think now most people are agreed this is just another emergent behavior of pattern-forming systems when you're sort of on the edge of enough one. Okay? But there were theories that the cause of this was, for example, there's certain species of termites that live here in these colonies underground, and they thought they were eating out root buds, and that was leading to basically these localized spots, and then they would go find another place and say these termites don't exist, so that can't be the cause, but then someone else would go and say, but there's ant colonies that do something similar, so that's the cause. And this is, again, still wrong, which is a little silly. And then on the bottom right, these are basically, actually these are the Negev Desert. This is Namibia. These are what we would call grass rings, and this is a grass spot, like the ferrosoliton. And again, you just see these in desert environments. These things emerge on their own. It's not like someone went and cut out the middle of those grass rings. So patterns occur all over in the natural world, even on the M, if you look closely. So it's about the right time. Do you see these little black things? Here, there's not very many of them. They're just sort of sitting. Here, you can see probably better on the TVs. They're jumping around. And they like to colonize, okay? So basically, if there's a bunch nearby, these things will jump towards them. And you'll get these nice localized patterns. And then when there's none around, you'll get they're pretty stationary. And you'll also see behavior. So here, there are way more of these. Basically, if you perturb these in some way, most patterns like this want to be round. You'll see it tries to return. There's some sense of surface tension, okay? So that's going to be important when we get to diffusion. So you see this thing is now coming back to a nice smooth. By the way, does anyone know what these are? Again, if you hike the M, there are certain spots where you'll find runoff and a bunch of these. They're called springtails or snow fleas. Okay? And it turns out the way they launch themselves is they pop their whole body. So that's how they're shooting from place to place to place. But it turns out these patterns you would study in a very, very similar way to all the ones I showed you just before. Okay, so fundamentally, mathematically, these things aren't really that different. All right. So when you're looking at pattern forming systems, often these patterns are a whole bunch of individuals acting in one way, where if you zoom out and look at it, it looks like some continuum. Okay, some continuous thing like those mud things when you were shaking it up and down, those oscillons. That is continuous, where those little particles on the right, the sand, you would think of the viewpoint on these things as like a bunch of little individual particles. You can see these that move around, they interact with each other, they have some sort of motion, they have some sort of attraction or repulsion to those things around them. Okay? And it turns out when you want to understand these things, sometimes you want to think of the individuals and sometimes you want to think of the big whole thing. Okay? So, turns out agents, agent-based models, there's a whole lot of standard pattern forming behavior. So this one, I think these are a bunch of sheep and that's a shepherd. I believe these are a bunch of geese, that's a person walking. These are a bunch of fish, and I believe it's seals going through. But one thing you see is these animals are all attracted to each other, so they want to be in a clump. But they're really afraid of something else, so they want to stay away. This is attractive repulsive behavior. Okay? So here it's a little hard to see, but there's more birds floating on the surface. There's an animal inside, and there's just this big separation. Right? And all of these basically are pretty standard systems that you actually can accept and understand. On the right here, we have what are called volvox. So this is thought to be one of the first species that ever evolved to basically have a whole bunch of cells working together. They're green algae in the ocean. And it turns out they form these big spheres that just sort of float around. And when they give birth to new volvox, basically those little volvox butt off inside and make these little small interior spheres. Okay? And then at some point, this big thing opens up a hole and they go out. There's also a very weird moment where you have an outside and inside on these things, and they have to actually fully invert or they will die. Which is weird. However, here, it's pretty clear you have a bunch of particles, but these things can be thought of as all behaving like some smooth sphere. Show you this video if I can. It won't go full screen. Okay, so this was a shepherd whose aunt passed away during COVID, and he was unable to go visit her, so he wanted to make some sort of basically memorial to her. He had a whole bunch of sheep, and so what he did is set his sheep up, and you see they were traveling in this big clump, and then he basically laid food out. And so these sheep were attracted to the food. They're also semi-attracted to each other, but they don't want to get too close. And so what you see is another one of these pattern-forming systems from basically attraction and repulsion. So one thing you see is when the density gets too high here, these sheep then decide to move on. They don't really know where to scatter, but they try to go away from other sheep, and then they will find more food. You'll get this nice phenomena where basically they collect on the heart. They try to uniformly scatter themselves out, but they're also really attracted to the food. You see that. Okay. So these are the sort of pattern forming systems that I want to give you some sense of basically how you understand them or the things that lead to them. So I said I would have to describe diffusion. right? Diffusion at some level is, I know you all know what diffusion is as a word, but it's more or less random motion of objects. And it turns out it's also related to wanting to make the outside of a surface smooth. Okay? It's actually related to the curvature of that surface mathematically, right? So basically, there was a botanist, Robert Brown, that in 1827, when you were first able to play around with microscopes, was looking under a microscope at a piece of pollen, and what he saw was it started to just sort of randomly kick around the entire time he was looking at it, all right? So, it was unpredictable, it was erratic, it was very random, and this is what is called Brownian motion. So if you look at like a particle undergoing Brownian motion, this is the sort of motion it makes. Okay? It will wander around, it will fill space eventually, but it does all sorts of weird stuff. Okay. So, particles that are moving under something like diffusion, or Brownian motion, will slowly wander around space in a random fashion. And effectively, it's like they're just taking a random step in some direction over and over and over again forever. So they call this orientation. And when you have a whole bunch of particles doing this, so you put Pepto-Bismol in a glass of water, you'll get slow diffusion out. That's called diffusion. And diffusion you think of as smoothing things out, okay? Random vibrations. If I give you a bucket full of sand that has a big peak in the middle, for example, and you shake it, what do you think is going to happen? It's going to go flat. All right. And it turns out, animals, people, all sorts of things, when they're looking for resources, especially in an environment they don't know that well, they diffuse. They just kind of randomly stuck around looking until they find something. So if you went looking for huckleberries, you might do this. Okay. Though, you'll often take what are called levee flights, or big jumps. So you'll wander around locally in a forest looking for chanterelles or something. You'll give up on an area, you know maybe there's mushrooms farther out that way, so you'll take a good quarter-mile walk, start doing the same thing locally. Okay. And this is what is called non-local diffusion. So, turns out animals are much more likely to do that than that. But chemical reactions are much more likely to do that if I set them up, for example, in a petri dish. Okay. So, it turns out the way we often try to understand these pattern-forming systems is what are called reaction diffusion equations. These are equations that will allow you to have multiple species. So for example, sharks and fish living in space. So you'll have some density of each of these populations. They wander around, so that leads to what's called a diffusion curve. And then they react. So it turns out if a shark catches a fish, they eat the fish. That's a reaction. That makes the fish go away and the shark is stronger. All right? So all of the patterns I've talked about basically can be understood from the standpoint of what are called reaction diffusion equations. Okay. And again, diffusion is just this propensity to wander around randomly. That's all it is. And the reactions are reactions. Things interact and something happens. So what causes Brownian motion? What causes individual particles like that pollen to bump all around? Basically, that pollen was sitting in fluid, and that fluid, more or less fundamentally, is always shaking around, right? If you zoom in on atoms, they're always banging around. So in this setting, those little metal balls are going to be water, and the big red thing is the pollen. And what you'll see is those little things shaking around, because they always do, lead to this weird erratic motion on the red thing. So Robert Brown, with his microscope, couldn't see the little metal balls. He could just see the big red thing, and that was the thing moving around in a weird way. Okay. So that is Brownian motion. So Robert Brown saw this in 1827. Anyone have a guess who figured out that this was happening? Einstein. Okay. So Einstein in 1905 basically wrote a series of papers that really fundamentally changed the understanding of our world. This included special relativity. So you know if you're accelerating, time does not move the same for you as for someone else. Okay. time is different on the moon than it is on Earth. Right? This came up in the news recently. But so in 1905, they called it basically his Annus Mirabilis. This was the miraculous year. Turns out, the thing he got the Nobel Prize for was not relativity at all. Okay? He was 25 when he wrote these papers, and one of them was basically understanding Brownian motion. So this is Einstein when he was 14, since when he was 61. He's a lot closer to this when he did all this work. Okay? So one of his discoveries was exactly what I just showed you on the previous slide, which is that Brownian motion came from this molecular heat map. Basically, atoms are always banging around, just because that's how thermodynamics and quantum mechanics work. And it was those things banging against this pollen that led to this weird erratic motion. And it turns out, with a lot of work, he was then more or less able to pull out important properties of things like atoms. So it turns out this was sort of the final verification of the atomic theory of matter. That was still up for debate in 1905. People thought there was still a continuum of matter. Some people think that was serious scientists working. And again, this was, as was shown in the previous video, related to more or less underlying temperature of gases or whatever things you're suspended in. And that's related to the speed of all of those individual gas particles banging into the bigger object. By the way, this was the same year, this was the same time that he wrote down E is equal to MC squared. Okay. So that's diffusion. That's Brownian motion. And so I said we needed a couple things to understand more or less these patterns. And diffusion was the important one. It turns out we usually think of diffusion as smoothing out things, right? I shake a bunch of sand, I expect it to go flat. But Alan Turing, this guy here, figured out that it could actually cause patterns to form. It could be the thing that drove these structured things to arise sort of randomly, all right? Turns out Alan Turing is better known as the father of modern computer science. He also, the movie The Imitation Game starring Benedict Cumberbatch was more or less about his work involving code breaking for the Allies in World War II. And it turns out he only wrote one paper on pattern formation. This was called The Chemical Basis of Morphogenesis. Morphogenesis is how, like, a ball of cells in a womb starts to develop a mouth and arms and legs and things like this, how it develops shape. Okay? So he wrote that paper in 1952, and sort of the key idea was diffusion coupled with sort of reactions and what we're going to call resonance was enough to make certain patterns get selected out and grow. Okay? Now, why he only wrote one paper in this is in 1952, that same year, he was convicted of what's called gross indecency. Basically, he was gay. He was robbed by a lover, and he went to the police and reported this. And they responded by arresting him. And then he was forced to choose between prison or chemical castration. So he took hormones and went chemical castration, became very, very depressed, and then killed himself eating a cyanide-laced apple a few years later. That's why he never published another paper in the field. It took until 2009 for the British government to apologize for this. All right, and then he was pardoned by the Queen in 2014. And then in 2019, he basically was put on the current 50-pound bill. Okay. So, as I said, one thing he realized was diffusion can actually lead to these selected patterns growing. And he formulated these ideas mathematically. Okay, so this is basically the main tool we have to understand how patterns emerge spontaneously from uniform stuff in nature. And this is why it's always in the settings of reaction diffusion equations. And again, the idea is very similar to basically resonance or harmonics. So more or less, systems will support certain structured things and not others. Okay, so what do I mean by that? Anyone play string instruments? I have a feeling most of you are just not answering. Okay. This is a sine wave generator. You have a string, things oscillate. And so it turns out, if I try to set up any sort of shape of that string and oscillate it, it won't stick around. Okay? But there are certain resonant ones. So these are basically the harmonics that will actually stick around as you vibrate this thing. So this is the second harmonic. You can get one that will have 3 peaks, but you're not going to get 3.5 peaks, 4 peaks, etc. Okay? So the main point is lots of physical systems have big global waves that are resonant, things that they want to stick around and will allow to stick around. And then they often have ones that they don't. So if you try to put the pattern of a wrong sort of wave number, so this is a spot with a wrong width that you somehow initially seed. So I set up a system that you would hope would allow me to have a spot this wide, the system will say no. Okay. So diffusion will help you start or kick off a pattern, and then this resonance lets that thing grow and stay. And to some degree, mathematically, those are the main instruments to understand what are called Turing instability, so like pattern forming instability. Okay, before I show you this, I want to explain this second. So these are a bunch of little particles, okay, that have a face. They have a direction, okay? So the idea is this, all right? Each of these particles feels every other particle in the system, so this is like a flock of birds flying around, correct? And they have some preferred distance and orientation. So for example, there's a whole room of people here. There is something keeping me somewhat attracted to you, which keeps me from walking all the way up here and trying to continue giving this talk. Okay? That is attractive. But if I get really, really close to someone and keep talking, that's pretty uncomfortable,
Yes.
right? There's a repulsion. So that's the first thing. And then I have a face, okay? So fundamentally, I don't want to stand here and face away. This is like the single person in the elevator facing the wrong way. Okay? So all of these particles, they're attracted to each other at a distance, but they don't want to get too close. That's uncomfortable. And they want to face each other. Okay. So that's all that's happening. These things have those things, a bunch of particles, and now we're going to let them move around. This is in 3 dimensions. What shape do you think I'm going to get by letting that happen?
Sphere.
Okay. So some people think a sphere. And what about directions? Are people going to face out, in, or some weird random collection?
Maybe in, it would be like a sphere facing inward, I just imagine. Makes sense.
Great. Everyone happy with that? And do you think there's any way by just changing how attracted I am to each of you or repulse, or how much I want to look in your face versus between you, I can change that? Okay. And if I do change that, do you have any idea what would happen?
Change the main size of the sphere, I believe. And
Dispersal.
So some say dispersal, some say size of sphere. So we're going to let this move. As it zooms in, as this thing runs, it's going to be easier to see the little yellow faces.
oh yeah.
And by the way, this was my first Ph.D. student at MSU's work.
Wow.
This was his thesis. So
That's right,
they're moving around. It sure looks like they're going to hit a sphere. And so one thing I should mention is this one here, for example, is repulsed by everyone here. But the bulk attraction to everyone else keeps them close. So you have this balance on far versus near side of the shape. And now it turns out, if you understand resonances, mathematically though, and you need some sort of what are called basis functions, you can now figure out how to adjust those sort of local attractions to choose out what pattern you use. Okay. So he's about to hit the sphere. We're going to spin it around so you can see what happens, then we're going to change the parameters. Okay. So that's pretty uniform sphere. This looks like those gold blocks. But now all we want to do is change how much I look at you versus between you. None of the other things. Just how much I want to face someone. This is what's called a mode 2. This is like that standing wave that had an up and a down. Just the 3D version. But now I can change how much I want to face each other a little more. And we'll get now effectively what's called a mode 3. This is like 3 ups and downs. So again, we weren't doing anything on an individual level. All of these particles are exactly alike. And this is just an emergent phenomenon that they all want to effectively interact in a similar way to each other, and it leads to these different patterns forming. I don't remember how long I let this video go on. The original was something like 7 minutes long. So this is just that resonance. This system wants different waves to exist. And basically, if you give it the chance, it will let those waves grow, and you'll get these interesting patterns out. And again, you can continue this for a long time. More or less, beforehand, figure out what sort of shape you want, and then make it happen. That's what this was. Okay. So, this is what's called the Swift-Hohenberg equation. I don't really want to talk about this at all, but this is fundamentally what's called a normal form. So all of those pattern-forming systems, at least at a certain point in phase space, they can be thought of as following this equation, which again, most of you probably don't know what any of these terms in this equation mean yet. That's fine. Okay. But this is, more or less, it was derived to understand if I heat a shallow thing of water, eventually it's going to give me these big convective rolls. So if you've ever boiled water, you might have seen that. This is trying to understand the start of it. And you get all of these different ring shapes. So this is a different way of viewing that, and spots. And this is a way of looking at whole families of solutions. It's called safety background. Anyway, this is the sort of equation people study when they want to understand more or less patterns in nature. That little triangle here, this is called the Laplacian. It's basically the term related to diffusion. And it turns out if I look at one of these solutions to equations like this, this is the sort of behavior that happens. I start with random noise, and I start to get these big these big regions of different states. So that is pattern formation. All right. Turns out in different mathematical models, you'll get spirals like this. So these are often used to understand things like heartbeats. Turns out you have these big scroll waves in your heart that initiate beats. And when you get breakup like this, this is more or less when you need to be saved because your heart is no longer beating. Okay? So often mathematically, the things we want to study are when patterns stick around versus why they go and how. Okay? Because again, it is important to things like this is a spiral wave, this is excitable media, this is does your heart continue beating? Okay, so I should probably try to speed this up and stop just because I think I've gone longer and started late. But I will say everything I told you is somewhat misleading. Okay? It's believed that reaction diffusion equations and these Turing instabilities are the main driver of log pattern formation in systems like this. But that's not so easy to prove because biological systems are extremely complex. So there's a guy, Shigeru Kondo at Osaka University. One of his big goals basically for his career was to prove reaction diffusion equations were more or less responsible for the formation of stripes on fish. So these are zebrafish, or most of these are not zebrafish, but most of what he studies was zebrafish. And so the experiments he did were more or less, I take a fish, and I have these things that are called, so this is just getting a reaction diffusion equation to the outcome. But he does what are called ablation experiments. So he would take a laser and burn off individual cells. This is a zebrafish in these things. Okay, so this is zooming in. He took a laser and killed off all the pigment cells. And then all he did was watch them regrow and saw what sort of patterns he come out with. And then he used a pretty simple reaction diffusion equation to show that if nothing else, and it's hard to see here, but you might be able to go on the screen, here it's better, that all of this sort of similar qualitative reproduction of those things could happen under simple reaction diffusion equations. So this is not proving that reaction diffusion equations are responsible for this pattern formation, but it at least shows that it's compatible with what happens in nature. So then people took that, and then they started to actually fit parameters on models for individual cells and how they grow and divide to data to try to reproduce more or less a zebrafish, but now a computational model that reproduces how the striping occurs. So this is a baby zebrafish. Why they're studied so much, they're a model animal for vertebrate development, is when they're growing, you can actually fully see through them and image them. And it turns out this is more or less, they have a pre-patterning of black and yellow cells. These are called monocultures, but anyway. And so they made this mathematical model based off of all of these experiments Congo did to produce effectively a zebrafish in the computer. Now, why do you care about this? One thing you can do easily mathematically that's really hard on a fish is change all the parameters for how things divide or move or anything else. Whereas if you're trying to do this on an actual growing zebrafish, this is genetic experiments with knockouts and things. And so now you can try to pull out fundamentally what are the underlying mechanisms that have to occur between cells to get the sort of patterns we see in these animals. So that is how mathematicians use these models. That's why they develop them. Okay. So this is, again, showing an artificial fish where I change various parameters. And you see, depending on these different parameters, only one really gives me nice stripes back. And adjusting any of these other fundamental things leads to different outcomes. Okay. And you can do this on actual zebrafish. So these are knockout experiments for zebrafish where, similarly to the last slide, they did genetic knockouts that changed more or less how these cells grow and develop. And what you could do was find all sorts of different behaviors that were more or less tied to a breakdown in pattern formation. Okay. By the way, she Boulevard has a Nobel Prize for this work. I said defects are hard. You can use similar models for zebrafish to understand stripe development and movement. So this is just a simple mathematical model for how these cells might move. And what you see is effectively what's called a moving defect pattern. That yellow thing is slowly migrating to the left. Also looks wildly inappropriate for a public lecture. And when I say instabilities, what I mean by that is if I start with a pattern the system does not want, and I just look later in time, what will happen is it will go away from that. So I start flat here. The system actually is pretty happy to have something not flat. So in time, it selects out this shape. Similarly here, this one basically wants a pattern to grow, whereas this one, these are all different parameters settings. Okay, this one takes this interesting shape and it just does not like it, so it dams it out. And we go back to the plastic. Okay, and I think that is actually probably a good place to stop. Anyone have any questions?
What is, like, is semantics what you were just, what's the difference between what you just shared and semantics? Like C-Y-M-A-T-I-C-S, semantics. It's like, I've seen, they'll put, it's like a water and then they have a vibration under it and it creates these like mandala effects of like the patterns on there. And I didn't know if it was like a field or anything.
So that is very much basically the same setting as this. Okay, just
Yeah.
different levels of vibration. You get different types of patterns out. You can understand them similarly, but you get different mathematical models out. Any other questions?
I saw that most of the examples provided were systems based on individual agents acting on each other, but I believe you also mentioned models that use that basically try to replicate the entire system. What are some
Okay.
examples of those?
So the only mathematical models I wrote down, like that equation, for example, that is all continuous. There are no individual particles. Turns out that one for the 3D patterns of these particles, the way you get there is by ignoring individual particles, and you're doing a density over a continuous thing.
That's interesting,
Yeah.
especially since okay.
And basically all those ones matching the zebrafish, other than kind of the one on the growing domain. And even those spiral waves, those are all continuous models.
Oh, okay.
Basically, understanding a bunch of individuals interacting is really, really hard until the number of those individuals goes to infinity.
Oh, okay. That makes sense.
So you use these what are called continuous or smooth limits, and that's what you can actually study.
Interesting. Thank you.
Any other questions?
Do you think this could be translated to like a human level of studying humans, like the way they move? Just I saw your hotspot in there. Yeah.
It is.
Yeah.
These continuous models, like there are continuous models for burglary hotspots that are used and for all sorts of human and animal behavior. And they're good for certain bulk things and very bad for other things.
Yeah.
Put it that way. So a lot of models for COVID, right? These epidemic models, they're not spatial, they're just time. But these are simple continuous models for the most part that produce really generic behavior that's in line with how an epidemic unfolds. And then you can come up with better and better models off of that. But yes, some version of this is used all the time for trying to understand
Like
human
socialization.
logical
Yeah.
behavior, socialization, etc. Not to the level of foundation. But
If there are no other questions, I can scan you in up here if you came a little late, and otherwise, thank you, Dr. McCalla.